So welcome to this Imoco training, and today we'll be discussing identification of frequency response function, and we'll discuss a more advanced technique that is very fast and also accurate, that even enables measuring above the Nyquist frequency. So I'm Max van Hagen, I'm from the Eindhoven University of Technology, and I'm also participating in an Imoco project, and I'm also representing my colleagues Lennart Blanke and Tom Ohme. Where Lennart Blanke is from SIUX and also the Eindhoven University of Technology, and Tom Ohme is from the Eindhoven University of Technology. So to start, why do we actually need a model? So typically in motion control, the challenge is to position our system G or our plant G accurately. For example, consider the Pilot 4 of Imoco. So actually the design of, for instance, the control structure, but also the feedback controller, and maybe even the feed-forward controller, they all completely depend on G. So a good model of the system G might be very beneficial for designing these three aspects of our controller. So then, of course, the main question results, how do we get such a model, and how do we get a good model of G? So a very traditional modeling technique is typically referred to as white box modeling. And what white box modeling is that we determine a model by utilizing system properties such as masses or maybe springs and first principles. Well, first principles, there's many modeling options available. The most simple way is maybe the Newton approach. The main law you would use is Fs m times a, probably well known to everybody. Using this, you can also get more complex expressions, for example, Euler-Lagrange, where we have mass matrices, Coriolis matrices, gravity matrices, etc. And recently, because of the increasing computational powers, you see a lot of finite element methods using CAD software. But you can think of many, so there's an infinite amount, I would say. However, in all these approaches, we have a very dominant commonality. And that is that what are actually the parameters, so the masses, the mass matrix, maybe the material properties in the finite element method, etc. And what model structure are we using? So a very simple Newton model, maybe more Euler-Lagrange type of model. So the key problem here in getting good models is that we have, first of all, uncertain parameters, and second of all, we have incomplete model. And that typically leads to actually an inaccurate model, and hence our complete control design might not be suitable for the real system. So a second option, which is done a lot in industry, is actually identify the system by measuring. So a general procedure will go something as follows. We create some sort of input U, and we excite the system with this. Then we measure the output Y, and we actually determine now G. So that can be a parametric model and use some prediction error method. Maybe we do subspace identification or frequency response functions, and there's again many more options here. But what the key idea between all these methods is that we want to determine a relationship between the input U and the output Y, or a mapping, so to say. And that is then our plant G. Well, this presentation will focus on frequency response functions only, which will be shown in the coming slides. So what is a frequency response function? So a frequency response function can be roughly summarized as just input over the output in the frequency domain. And the key idea behind this is that if you put one frequency in, you get the same frequency out. And that's actually, for a linear time invariant system, this always holds true. So let's say we have again the system G here in the middle, and we create the input U. That's just one sinusoid of one frequency. If we take it to the frequency domain by using the Fourier transform, we get only the single value on the frequency of the sinusoid. Well, if we excite, this input on the system, we would get the output out, which is actually of the same frequency as the input, just maybe with some gain and phase differences. Also, if we take the Fourier transform of this signal, we again get only a single value on this frequency. Now, this frequency response function is actually the gain, so the factor between the input and the output, which in this case results to this pole over here. Now, what we can do is we increase the frequency. So now we put 2 periods in the signal. Hence, we have a higher frequency here, we have a higher frequency here, etc. And we determine the gain at these frequencies. Okay, well, let's do another frequency, a bit higher again, etc. We see, hey, the gain is slightly higher this time. Okay, we put our data point a little bit higher. Now we can do this for all frequencies, and then we can nicely create this green frequency response function as shown over here. So now let's take a look at frequency response function identification during transient condition. So what I briefly showed on a previous slide is that one of the assumptions of the frequency response function is one frequency in and another frequency out. And this is typically also referred to as steady state. So if we again consider some input signal of a sinusoid with a single frequency, which in the frequency domain has only a single value, we take a look at the output, we actually see that in the beginning of our signal, we have some sort of transient period, this is referred to. So we're not fully in steady state yet. If we take a Fourier transform of this signal, we see that not only one frequency remains, but we have some harmonics, some other components left over here. And we typically refer to this as leakage, or leakage due to transient conditions. Well, if we would try to estimate a frequency response function using this data, you can see that we would have a mismatch between the true FRF and our estimated FRF, because actually signal is literally leaking from this frequency to other frequencies. Now, what you could do, for example, is say, okay, let's remove this transient part. We will only take a look at the steady state, both for the input and the output. And if you take a Fourier transform, you would get the original output again, and also the original system at that frequency. However, the key problem here is that if we need to do this for all frequencies, we need to remove the transient period. We significantly increase the measurement time. Especially for systems like thermal systems, this is really detrimental to the measurement time. So now let's take a look at a second example, and that's frequency response function identification under aliased conditions. So what is aliasing? Actually, it means that signals above the Nyquist frequencies are mapped to lower frequencies. For example, again, if we take a look at the pilot 4 from Himoco, with input-output behavior, U and Y. But now we take a look at the linear scale frequency response function, because it's slightly easier to interpret in this case. And you apply a relatively fast sinusoid over here. Again, in the frequency domain, it has only a single component. So in the output, we would also see the single component. So we're, for now, assuming a steady state behavior. If we do this, again, similarly to the previous slides, we can easily reconstruct the system at that frequency. Now, let's take a look if we actually work with sample data. So now the blue dots are samples of the data. Everything would look the same. So the discrete Fourier transform would look now like, again, this single pole, same for the output. Now, let's downsample the output. Maybe because we are using, for example, a camera that cannot sample as fast as a normal encoder, for example, would be. And that means that only every 3 samples are available. You can clearly see now that there is a different frequency content in the signal. It's a lot slower, actually. And also, if we take a look at the Fourier transform, we see there is a difference between actually the original signal and the new signal. And this we refer to actually as aliasing. And actually the difference between these peaks is in this case specified by the sampling frequency over f, and because we use every 3 samples, this f is equal to 3. Well, and of course, if we would try to estimate our system at that frequency, we would have a complete mismatch with the true system. So now let's take a look at slightly more complex example. So our input now looks as follows, and it's actually a combination of 3 sinusoids. So we have these 3 frequencies that we are exciting. Well, if we take a look at our output on the fast rate, so y, we would have the following frequency content, time content. And if we convert that to the frequency domain by the Fourier transform, you see the following output. Well, we could nicely reconstruct the plant with the signal, but again, let's assume that we only have the slow sampled values, so every 1 out of 3 samples. And again, you can clearly see that actually the signal contains only 1 frequency. So in the time domain, this is here, this sinusoid, and in the frequency domain, you only have this data point over here. And what you see is that the outputs, so the fast outputs y, are actually somehow entangled in a single output. And that makes it that we cannot disentangle the individual components. And then if we try to estimate our system, even at the lower frequency, we would get a complete mismatch of the system, which is of course highly undesirable. So the key problem here, what we identify with traditional system identification, is that identification is impossible due to aliasing. Sampling is too slow. So now I want to discuss local parametric modeling, which is a more advanced identification technique which can solve both key problems. So the first key problem is that transient time significantly increases measurement time, and the second key problem is that we cannot identify due to aliasing conditions. So what is local parametric modeling? So what we do is we fit a local model in the frequency domain. There's a very short example here, which I'll come back to later. And you can see that the frequency response function in red is being fitted with this green line locally in the gray window. What we do here is we actually exploit the smoothness of frequency response functions, which is a very powerful concept and done a lot in literature. The potentials of LPM are endless, I would say. For example, we can actually suppress the transient and input leakage. We can do single experiment, multiple input, multiple output identification. And we can even identify systems above the Nyquist frequency. This presentation I will focus again on the transient suppression and also identification above the Nyquist frequency, which I'll explain in the coming slides. So I want to first dive a little bit deeper into frequency response function identification during transient condition. And the key assumption of the standard frequency response function is that we have one frequency out is one frequency in u. And here the omega k is a discrete frequency. And what we see is that we have one unknown, right? So we have the system G at the frequency omega k. And we have one equation, so y omega k, and of course we also have u. So what we see here is that we have an equal number of unknowns and a number of equations. That means that this system of equations is solvable. If we want to get G, we just divide y by u. In transient conditions, however, what we see is that actually our input-output behavior is that the output y is both dependent on our system G, but also on our transient t. And what we now have is two unknowns. So we have our system g and our transient t, but only one equation. Again, we still only have this data point y. So what we see, the key problem is that we have insufficient data for the number of unknowns, and hence this transient is not suppressed in traditional frequency response function identification. So what LPM actually does, it utilizes neighboring frequency data and smoothness. So consider again the transient condition, where our output is a combination of the system, the input, and the transient, where you can see actually the graphical representation of this over here, right? So in green we have the system G, we have in blue the transient, and then the output Y is some combination of these two. Now let's create some sort of window, right? K and K plus 1, where K is a frequency now, 120 Hertz, and K plus 1 includes the next frequency, right? And in this window we are going to approximate our systems G and T. Well, we do that, for example, just very naively saying our system and transient are roughly constant in these regions, right? So we have these two red lines in the plot. Well, now we can actually approximate the output in this window using these two unknowns, right? So we have our approximated planned G hat and our approximated transient. So we only have two unknowns in this frequency window. Hey, but because we created this window, we actually have two data points now. So Y at the frequency K, but also Y at the frequency K plus 1. So what we see here is now the number of unknowns is actually equal to the number of equations. And then our mathematician in us would say this system of equations is solvable. Of course, it might be too naive to say that our system is constant at the frequencies. As you can see here, we have quite a significant mismatch between the real system in green. But LPM completely enables more complex local models. For example, linear, maybe a polynomial model, even rational models are available. What you saw already was that we get more unknowns, right? For example, for the linear, we also need to estimate the slope. And that means that we also need to have a larger window, which you saw in the illustration. But the typical choice might be to create a polynomial model with a second degree polynomial. So how does this actually look like? So for the system here in red, we're going to create a window, and in this window we're going to fit a polynomial here in green, and then for the central frequency we're going to set the value, right? And then we will move over the window to the next frequency and keep on moving. So I'll just show a brief animation now. And as you can see, as our window is sliding, we will getting system estimates at the central frequency. And then at the end, all our frequencies are estimated. So if we take a look at the end result, we see here in blue the LPM. We have quite a good result. But if we apply a traditional frequency response function using a Hanning window, we get the purple, so it's much worse. So let's move on to a little bit more practical example. And in this case, we're going to identify a sensitivity function. So the sensitivity frequency response function is shown here in the top. And in the bottom, we will see the modeling error of the different methods. For the LPM method, we're going to use a polynomial model with order 2. So if we apply a traditional frequency response function with a boxcar window, you can clearly see in the top plot here that for lower frequencies below 2 Hz, we are actually estimating the transient instead of the system itself, which is of course very undesirable. If we apply a Hanning window, we can already significantly reduce the effect that the transient in yellow has on the frequency response function, and we get a much closer result to the true system. If we now apply the local parametric modeling technique, we can see that we have a very good estimate for low frequencies. But additionally, we also have a very good estimate for higher frequencies, which is now illustrated here in the error plot, where you can see that green has the lowest error for actually all frequencies. So to conclude, local parametric modeling exploits the smoothness of a system to estimate more unknowns, and that enables both transient suppression but also accurate and fast identification. So now let's take a look at a second example. So if we take a look at the input-output behavior of a system that is downsampled or slowly sampled and neglecting the transient, we see that our output y is actually a function, a summation of system and input terms. And this was illustrated by the figure where you saw that on the fast rate, multiple outputs were mapped to one output in the end. And for this setup, we can also create a system of equations, where in this case we have again one equation or data point, y, but we have f unknowns, so that would be the system terms at the different frequencies. So for this case, the number of unknowns would be higher than the number of equations, and hence the system of equations is not solvable for G. But as we learned previously, we can really easily solve this by local parametric modeling. So this is a little bit more tricky than the previous example. So now we again have these local windows, these grayed out local windows, but we have them at multiple frequency regions because we are analyzing these aliased conditions. So within these windows, we are actually fitting these green polynomials, right, over here and over here, and then moving the bins over, which I will shortly animate right now. So as you see, our windows are sliding from left to right, and there's polynomials being fitted, and then the central gain is being recorded. And as you can see, the system is being estimated quite accurately, especially if you consider that the Nyquist frequency is located over here. So that's only 175 Hertz, if I remember correctly. But above the Nyquist, we still have a very accurate estimate of the system. So let's again move on to a little bit more concrete example with an experimental setup. So the identification setup is actually a 2-mass spring damper system, as is shown here in the picture and the schematic setup. And what we're going to do is we're going to apply an input, record the output, and then downsample it by a factor 4. The number of samples we record in the input is actually about 14,000 and the output less than 4,000. And we're going to compare several methods of identification. So of course a traditional method, the developed method, and the developed method, yes. The fast sampled output Y is also available, but it's only used for validation of the framework. So let's also take a look at a more concrete example for identification of the Nyquist frequency. So if we take a look at the traditional frequency response function for this downsampled system, we would get the orange line shown over here. And the blue line is actually the true system. What you can clearly see is that aliasing causes the resonance around 18 Hz to dominate the identified response. And this is a clear mismatch in the system estimate, especially at the yellow circles here. If you now apply the developed approach, you can clearly see that the orange line, the estimated frequency response function, is quite close to the real response of the system. And you can clearly see that the estimate is superior with respect to the traditional FRF, especially considering that the resonance is identified clearly and also some higher frequent parts over here. Especially considering that the Nyquist frequency is only 15 Hz here, and even up to a factor of 4 above the Nyquist frequency, we can still identify quite accurately. And finally, maybe you've already noticed, but the green line here indicates the variance, and that's actually directly enabled by the developed framework. So to conclude, LPM exploits smoothness to estimate more unknowns, which includes transient suppression and fast and accurate identification, but thirdly can also identify systems above the Nyquist frequency. Well, then I quickly like to summarize. So LPM, we exploit smoothness that enables transient suppression, fast and accurate identification, but also identification above the Nyquist frequency. I didn't show it this presentation, but additionally we can also do single experiment MIMO identification. And finally, the experimental results clearly show the potential of LPM. I'd like to thank you for being at the training, and good luck.